resources that would have been wasted on, this arms race trying to get, sort of think about like this, who's going to be taller here? The arms race to get taller than one's neighbors, when you have a whole field that are the same genotype, that kind of arms race is clearly mutually assured destruction. There's some strange things in the phenotypes discussed very well in the paper. There are effects on transpiration and so on, so it may not be just, this may in fact be a complex trade-off, not the kind of simple trade-off that we'd expect just from conservation of matter. Donald and Yuan were pretty much in agreement with John Sheehy, for example, about the importance of erect leaves. And John discussed this pretty well, but maybe not everyone was there, so I'll sort of go through this. And the key point here is that this erect leaf trait is one that's really linked to trade-offs. It's not that erect leaves are better under all conditions. It's that they're better under high-density conditions. And high-density conditions are where we have the maximum yield potential. So if we compare these two cartoons at left, this erect leaf cultivar missed that photon. That photon went down here, didn't hit a leaf, didn't contribute to photosynthesis. Came down here, and you see I've got some water here because this is a rice paddy. Evaporated some water, wasted water that was not contributing to photosynthesis, whereas a horizontal leaf cultivar spread its leaves out more and intercepted more of the solar radiation. But we can achieve the same end with erect leaf cultivars simply by growing them at a higher plant density. So here we have complete light interception by the erect leaf cultivar is spreading the light over a larger area. And because C3 photosynthesis in particular tends to saturate at high light, there's no point in having your upper leaves having twice as much light as they can use. It makes much better to spread the light over all of the leaves. Here what I've drawn is what happens if you take a horizontal leaf cultivar and tilt it up at an angle. It's only getting half as much light, but that results in only slightly less photosynthesis per square centimeter. But you have twice as many square centimeters illuminated, so the overall effect on photosynthesis is positive. So that's all theory, but here are some data. I don't actually remember what species this is for, maybe somebody knows, but this is a comparison, not for granule, but for biomass, and comparing erect and horizontal leafed genotypes at low and high density. At low density, consistent with the theory in the previous slide, the erect leaf actually produces less biomass, presumably because with erect leaves, they're not intercepting all the available solar radiation, or at least not as early as the horizontal leaf cultivar does. But as you go to higher plant density, both genotypes have complete light interception, and the erect leaf cultivar is using that, is illuminating a larger fraction, it's spreading the light over a larger fraction of its leaf area, and therefore has higher photosynthesis and higher yield. Here's another example. This, I think, is for maize. The vertical axis is both biomass yield and grain yield. Leaf area index, so leaf area index of 1 means there's 1 acre or 1 hectare of leaf area per hectare of land. And actually, in this experiment, they didn't do anything below leaf area index 2. So if there's a trade-off there, we're not going to see it. The low density trade-off. But at the range that they looked at, up at the higher densities, the higher leaf areas, the erect leaf had substantially higher biomass production than the horizontal leaf. And the same thing was true for grain yield. And in fact, you see a decline here at high varied index in the horizontal leaf cultivar. So the erect leaf that was advocated by both Donald and Yuan et al. Seems to be pretty good as long as you're going to have the plants at high density. It does seem to be a superior trait. And once again, selection for yield appears to have improved this trait without deliberate selection for leaf angle. Oops. So this is the leaf angle score. Again, year of introduction, and these are different maize genotypes. So we're seeing this a lot, that selection for yield is good at increasing yield, as Yuan et al. Concluded, but also that selection for yield seems to be giving us the kind of idiotype traits that Donald hypothesized would be associated with high yield, at least high yield at high plant density, high soil fertility, and so on. So the question this raises, which I'll mention now in case I forget, if selection for yield is going to give you all the benefits that you could get from selection for idiotype traits, is it better to select for yield? And then the question is, well, okay, 60 years is kind of a long time. Could they have made faster progress if they used an idiotype approach? I don't actually know the answer to that, but something to think about. Finally, the most controversial of Donald's traits was to really reduce the amount of tillering and ultimately even go perhaps to a single stem genotype of wheat. And there was nothing like that in Yuan's idiotype. The space I occupied here was having the panicle inside the canopy, which would actually be similar perhaps to some of the issues I talked about with the tassels, shading the crop. It might be better not to have, even if the panicle has a little bit of photosynthesis, you don't necessarily want it shading the leaves. So that seems like a good idea, but I won't say anything more about it. Well, what about this stem number business? Certainly, in the domestication of maize, we went from Teosinte, which is a highly branched and very low yielding plant, to a single stem maize with much higher yield. Similarly, for sunflower, the wild sunflower is highly branched, and the modern cultivated sunflower is a single stem plant. So, okay, but what about wheat and rice? Well, I've got data from Austin on wheat at the left. The vertical axis, again, is yield. The horizontal axis, not stems per plant, but stems per square meter, so at least related to the number of stems per plant, since the number of plants per square meter was constant in their experiments. And in wheat, we see exactly the relationship that Donald predicted, that is, having more stems per square meter decreases yield rather than increasing. But in Yuan's results, we see exactly the opposite. Only 2 of these seasons had a statistically significant relationship, but both of those were positive, and if I had to guess, this looks like it's trending in a positive direction. So for the idiotype trait of how many stems should we have per plant, we seem to have a discrepancy between wheat, where Donald's prediction was borne out, and rice, where it was not. Once again, though, this is a trait, the optimal number of stems per plant really depends on your plant density. If you have only widely spaced plants, then you better have a lot of tillering to fill in the available space. But if you have widely spaced plants, even with high tillering potential, it's going to take them a while to fill in the available space, intercept the available light. Whereas if you have plants with fewer stems per plant, but grown closer together, you're going to get earlier canopy closure and intercept a larger fraction of the seasonal solar radiation, therefore potentially having greater yield potential. Or so it seems to me. And there's not much data on this. This study from Kokobun is actually for soybean. And what he did was to grow a normal soybean cultivar, which does tend to branch over a range of plant densities, and didn't see much change in yield over that range of plant densities. And then he used a razor blade, or maybe he used a graduate student with a razor blade, I don't know, to make a bunch of single stem soybeans and planted them over a range of plant densities. And there we see exactly what you would expect from the kind of trade-offs that Donald talked about, what I've just been talking about. That is, at low plant density, the non-branching soybeans are not able to intercept all the available light in the same sense that an erect leaf, wouldn't intercept all the available light at low density. But as you go to higher densities, the single stem lines come into their own and perhaps intercept the total solar radiation earlier, or have fewer wasteful stems that never get enough resources to make seeds, or whatever. At any rate, results consistent with Donald's idea for soybean. So, to summarize, I'm not sure if this is the end of my talk or not, but I guess we'll find out. To summarize, I think trade-offs are key to idiotypes. It's not just a matter of saying, these are the traits that my intuition tells me we should have. That you really need some detailed analysis to figure out what kinds of traits would be appropriate in an idiotype. And then even with analysis by smart people, perhaps armed with computer programs, we really want to look at the kinds of data that I showed from Austin and from Yuan et al. To say, okay, we think that this trait ought to increase yield, but does it? Produce plants with a range of those traits, grow them under high and low density, and then plot your yield as a function of the number of stomata per square centimeter of leaf, or whatever the idiotype trait might be, and see whether your intuition and your analysis is in fact borne out before committing to using that trait. So, but it does look like what I've showed today that harvest index is a superior trait to seed weight or some component of harvest index in terms of predicted yield. But then we start getting into what's better under what kinds of conditions. The data that I showed suggests that shorter is better, but certainly that would depend on having good weed control. Otherwise, shorter would be worse. And I'm not saying we should neglect the concerns that John Sheehy raised the other day. That's certainly we do need some place to put the nitrogen. The question is, what are the implications of that for plant height? Erect leaves seem to be consistently better, as suggested both by the theoretical analysis and the data for numerous species, but they're only better at high density. So you could easily go out and compare a bunch of erect leaf and horizontal leaf cultivars and have the horizontal leaf cultivars come out with higher yield. All you have to do is grow them low density, and erect leaf cultivars are going to fail. And similarly, fewer stems per plant seems like it has potential at least, but it's only going to work well at high density. So then the question is in rice, what's the feasibility of going to closer spacing than the 20 centimeters or so that's typical now? So I'm not really going to try to convince you, because I don't have a definite opinion myself, whether breeding for yield or an idiotype approach based on trade-offs, which of those is going to be superior when you consider all the factors that go into the process. Okay, if we want to breed for yield, we really have to worry about edge effects, so we're going to have pretty big plots. Whereas if we're going for idiotype traits, we may be able to assess them from just a single plant or just a few plants. On the other hand, if we're doing the idiotype traits, maybe we're missing something really good that would have shown up in the breeding for yield approach. So I can really see both sides of the argument. I think it's an important argument to have, and even though I had some questions about some of the specifics in Yuan's paper, I think that's, it's really the state of the art, and that's the kind of foundation that we can build on for this kind of discussion. The one thing that I would say, I put this slide together before I got on the plane and came here, is that for either idiotype traits or breeding for yield, it's really worth thinking about, are there more efficient, more powerful ways to assess these kinds of traits? Electronic instrumentation, sensors, all that kind of, computer power, all that stuff's getting cheaper. Drones that can, go and fly a raster pattern over a field with little sensors, looking down at the crop, those are getting cheaper. And so I was going to tell you that you ought to be doing that kind of thing here. This is a image of vegetation index image from the uniformity trial at the long-term experiment that I ran at UC Davis. These are 1 acre, so half-hectare plots or something like that. And it was really informative to grow the crop up. This is actually the time when we had canopy closure, so these differences we're seeing reflect differences in chlorophyll content of the leaf, which in turn are due to underlying differences in soil properties. You see this line here. That was an old water course, which when the field was leveled, was filled with high organic matter topsoil. So it has higher fertility. And years later, we could see that line going through the plots, and we're really glad that we had this time zero data, so that we knew that it wasn't that Israel had driven, diagonally across the plot, with the manure wagon or something like that. And then this is a thermal infrared image from the same, from years later, when we had irrigated, lightly irrigated, and non-irrigated plots, and you can see that showing up in leaf temperature. So anyway, I came here prepared to tell you that you want to be doing this sort of thing, and I was pleased to find out that you are. So thanks very much, and I'd be happy to take questions.